You're currently in the Jasmine Room for Internet Scale Malware Analysis with Zachary Hanif, Tomas Lengel, and George Webster.
Hi guys, we'll be discussing Internet Scale Malware Analysis. So during the talk, we're going to briefly discuss who we are, kind of the motivation, the problem as we see it, and we're going to discuss the framework which we believe will help solve this problem and alleviate it. We'll then be discussing 2 different implementations and discuss what we're going to be trying to do with this in the future. So up here we have Zachary Hanif. He's the Director of Applied Data Sciences at Novetta. He's also a co-author of Binary Pig, which is a feature extraction for large-scale static analysis. We also have Tomas Lengel. He's a PhD student at the University of Connecticut. He's a senior security researcher at Novetta, and he's the creator of Dracuf, which is pretty much for large-scale dynamic analysis through virtual machine introspection. And then you have me. I'm George Webster. I'm a PhD student at the Technische Universität of Munich, and I'm researching the cognitive bias in cyber defense. So what we really have for our motivation is we wanted to create a system that really incorporated the full scale of the analytics lifecycle. And we wanted to do this across multiple teams. So we needed the system to be very fast. We needed it to be scalable. We wanted it to be resilient. We wanted it to be flexible. And by flexible, I mean we want to be able to incorporate new analytic methods and techniques pretty much with ease. So what we did was we developed Scalid. When Scalid is just basically an architectural blueprint for saying, this is how we need to design our system, this is what we need to create. We then did Totem, which is a scalable static analysis implementation. And then we said, hey, we need to take Dracuf for dynamic analysis and figure out how to tie this all into the system together. And Dracuf is done with the hypervisor, and it needs no in-guest agent, and it's quite nice. So to kind of discuss the problem is really the current state of affairs, and as you guys are all well aware, it's absolutely like a tsunami. And this is for multiple reasons, which we'll discuss shortly, but really it's because we can't keep up. So in 2012, McAfee stated that we receive 200,000 unique samples a day. However, in May in 2015, VirusTotal was saying that we were receiving 1 million samples a day. And this doesn't even talk about the historic data that we have and trying to process all that information as well. Furthermore, our tools are absolutely disjointed. They're pretty much one-shot wonders, trying to solve the problem for what they need to do at that time, not really looking at how do you tie this into the big picture of things. There's also heavy reliance on the individual analyst and a single person to try to tie it all together and figure out what's really going on. Furthermore, our tools are only focused on the binary. This came a lot from the antivirus community, but the problem with that is you got multi-stage droppers, you got metamorphic malware, you got polymorphism, and really at the end of the day, creating a new binary, creating a new sample is absolutely dirt cheap, and it's just, you can't keep up. Furthermore, you got your defensive tools are all focused on that signature. So these binaries that can't keep up with, you got the defensive tools are trying to create signatures for those binaries. So if you look at Snort, AV products, Yara rules, you just really can't keep up. So the current state of affairs is getting even worse with kind of the rise of the actors. You got organized crime, you got nation states, and these guys are very sophisticated, they're very smart, they definitely know what they're doing, and now they have a lot of resources. So malware no longer is existing in a vacuum. You really have teams that are dealing with sophisticated tools. You got large-scale infrastructure that's very complex. You have analysts telling them what to do, how to do it, and where to do it. And you also have financial networks that are moving the money around. So what this really means is your reverse engineer, he's really not enough. So we really need to get pretty much going back to the initial analytic life cycle and say we need to focus on the 5 W's. We need to focus on who's behind the action, what are their goals, where is the infrastructure, when do they operate, why are they conducting this operation, and most importantly, how do we stop the activity? So lastly, we're really in the age of big data, and we need to figure out how to leverage our defensive tools to actually take advantage of some of these techniques, take advantage of this data that we have. And we need to use multiple tools and different techniques to do this. One thing's not going to do it for us. So we need to use machine learning. We need to do graphical representation. We also need to do reverse engineering across what we get. So as we sat there, we looked at the problem and said, really, we got two ways to go forward. One is we stick what we currently have, and we're going to get failure, or we probably already have it. Or two, we try to figure out something else, try to go in a different direction, maybe have some success. So in order to try to go to the success path, what we did was we created Scaled. And Scaled is really a microservices framework that is basically made to conduct the full analytic life cycle and provide the infrastructure needed. So we wanted to support hundreds of millions of objects, allow it to automatically expand over public and private infrastructure, pretty much the cloud. We also wanted to provide the infrastructure to not only gather all the features that we need, but also to provide the infrastructure to then do something with that data. We also wanted to support third parties, so if you're dealing with VirusTotal, Threat Connect, or all these great places, that it can bring this stuff into the system. And even though the tools are disjointed, it doesn't mean that they're not valuable and they're not important. So instead of having to rewrite the wheel, we wanted to be able to incorporate all that stuff back into the systems. So when we look at Scaled, we really broke the system down into three core components. And these components are the transport layer, your planner, and then your services. So the goal of the service is to perform an individual task independently of each other, kind of an atomic nature. And we wanted them to only interact with the planner. Next, with the planner, we wanted to schedule the service's execution and figure out if something's going wrong with the service, fix it. If anything needs to be restarted, restart it, and then kind of manage all that together, but do it in a smart way where it actually figures out how do we do this best so we're not just wasting our cycles. Furthermore, we wanted a planner we wanted a transport layer that can actually move everything around between the planners and do this in a scheduled way to kind of make it so we can't really lose data. So looking at Scaled, this is pretty much the big picture. And with the big picture, there's 5 main themes. You got your gateway, your storage, your investigation, your interrogation, and your presentation themes. In this talk, we're really going to talk about the investigation and the interrogation levels. So with the interrogation planner, the goal here is to figure out when you receive a sample, when you receive an IP address, a domain, what is it and what information can you get from it? So this really focuses on just one object, be whatever it is, it's agnostic. But how do you do the static analysis, perform the dynamic analysis, get information from your third parties, and kind of put everything together? So let's say you got a sample, this will execute Cuckoo, this will pull into Dracu for dynamic analysis, PE info, VirusTotal, or whatever have you. Next is you get a huge amount of data, and you got a lot of features that are generated from this. So what do you do with all that data? How do you display it? What do you work with it? From there, we have the investigation planner. This is broken down into 2 parts. The first is you're dealing with a tremendous amount of data, so you need to provide an infrastructure to figure out what's going on. And this incorporates machine learning and static analysis to say, hey, how do we cluster our stuff together? Do we see any patterns across data that we have? What is the behavior? How is everything functioning? So how do we do that on that level? Next is we're dealing with humans, and our human analysts are very good. So we wanted to be able to say, what do we do and how do we provide this data to these people in a way that makes sense for that individual, not in a way that makes sense for the person that created it. So we wanted to be able to provide services that can provide an API interface, plug into a web portal. So if you had, say, IDA Pro, you could just provide a service that provides the data you need into IDA Pro. If you had Maltego, just add a little service that provides an API, so now your data could be displayed in Maltego. The goal here was to display the data in a way that's best for the analyst, best for the end user, and could tie into your existing tools. So with Scaled, what we really did, we created a framework, and the framework provides a general overview. So going forward in this talk, we're going to provide kind of 2 different styles of implementation. The first is going to be static analysis, and then the second is going to be the dynamic analysis piece. To start talking about the static analysis implementation, I'm going to hand it off to Zach, and he's going to discuss Totem.
So Totem is the first planner that we implemented that effectively controls how we consume work what work needs to be done and how we monitor the work that needs to be performed. Totem can be thought of both as the planner, the thing that coordinates all of the individual elements of work and all we need to do, as well as the static analysis components which directly plug into it. So Totem represents our static analysis process for very large file data sets. Right now, Novetta, which is where I'm working, receives middling six figures worth of malware every day. For those of you from a large AV or one of the infrastructure owners, I'm sure that's not what you would consider to be extremely large amounts of malware. But that's what we get in a streaming process on a daily basis. And we evaluated a number of different open source malware zoo and malware instrumentation engines to try and figure out if anything that's already existing out there would work for us. And what we found was more or less nothing out there right now is able to consume streaming amounts of data at the volumes that we need it for the kind of analytics that we need to perform. The other thing that we started noticing as well in the process of doing a handful of directed operations over the course of this last year was that a lot of our partners in the AV industry or in the larger security industry, some of them had serious problems being able to run historical signatures or historical analytics against their malware store. Obviously, anyone's going to have issues running any kind of analytic against 200, 300 million malware samples. But we were finding that they probably couldn't even go back more than a week or two in many cases. And so what we identified was we needed to develop some way to allow us not just to ingest the ongoing sets of malware that we have right now, but to also be able to apply new analytics and new findings against the historical malware sets that we have. Because if you can't look back, what good are your models at the end of the day? In addition to that, we identified a handful of other design requirements that we had. We needed to be able to have dynamically defined jobs. And by that I mean, let's say a piece of malware comes in and we know for whatever various reasons we have, we only need to run it against one or two different analytics. Whereas another piece of malware that we collect might need to be run against 7 or 8 or even 9, any arbitrary number that we have. You can't set up a system that has one particular path of execution through the overall analytics stream. You need to be able to route things dynamically. You effectively have these small graphs that get created so that you're able to say, okay, if this result is such and such, you run it against this other analytic. And then finally, we needed to be able to dynamically scale this system. The other thing that we found when interacting with other people in the larger malware community was when doing static analysis, we found a lot of people who would size clusters based on either the spike that they get on every single day when new malware comes in, or they would size it against some known quantity that they'd be getting every day on average. And respectively, this leads to either you have an underutilized cluster or a cluster that you have to continuously resize every single time you go up another 10 or 20% in your average number of malware samples you've collected a day. So we implemented it along the same time as we began to define the Scald framework, and we've ended up with an asynchronous and easily extendable system that lets us scale very well and be resilient to failures in a distributed environment. So calling back to the graph we saw a little bit earlier between the transport planner and service layers, this is how we've implemented it in terms of Totem. Our transport layer is handled by RabbitMQ. The transport layer is where we load new samples into, or at least tell the system that there are new samples that need to be processed. We're using RabbitMQ for a handful of reasons, and they're all very practical. At the end of the day, it's a very well understood, well supported system. Every major language has bindings for it, and most of the bindings are actually very good. I'd imagine that probably, I don't know, a third to half of the people in here have probably used it or heard of it in some way at some point in time. And this allows us to asynchronously load malware, hold it for work, and then have new workers join. There are a couple of very nice things about Rabbit, aside from the fact that it's easy to understand and easy to work with. Probably the biggest one of it is it's very easy to scale the system as a whole. Right now, we're capable of ingesting probably north of 7,000 malware samples a second during our current deployment, which is more than fast enough for our average streaming process. What we're able to do with that is quickly ingest a large amount of malware. But when we come to stages where we need to ingest even further, not only can we add on more submitters to the system, we're capable of horizontally scaling Rabbit itself. It's got high availability for those of you who need some kind of high availability system, and then you're also able able to distribute the queues themselves so that you can have dedicated nodes working on a single queue and all sorts of other fun things. The other piece of functionality that we really rely on very heavily inside of Rabbit is that it's got a very deep routing topology system. It's very easy to insert various ways to route samples through RabbitMQ while being able to maintain a level of persistence in the system. In the event that we lose a Rabbit node, in the event we lose a worker, we never actually lose any kind of meaningful work. We always remember that there were several jobs that were queued that we need to process, that malware needs to be pushed through. We never actually lose any kind of maintained state. The next part of the chain really then is the planner, which is the totem worker itself. It's the largest collection of state overall in the system. It manages RabbitMQ communications. It organizes, verifies, and validates results once they've come in. It ensures that downloads of the individual malware samples themselves happen at speed, and it does all of the communication with the individual analytical services. Overall, this is our major workhorse. It's got a lot of interesting properties. If any single worker fails, messages are persisted to disk. If a particular set of analytics fails about halfway through the analytical set, anything that succeeded gets serialized out, gets stored for database use later, and anything that failed will simply get bundled back up and re-queued again. And this keeps us from having to do multiple retransmissions or retransmissions in different areas all for the same set of analytics. And this seriously cuts down on the amount of network traffic that we have overall and speeds up what we have. Finally, we've got the services themselves. They're based off of basic RESTful wrappers around known tools or things that are developed internally to the consumer. We made this decision for a couple of reasons. Yes, HTTP is not the fastest thing out there, and yes, you could definitely have implemented it using, say, Protobufs or Avro or even Thrift or something along those lines, a more traditional IPC system. But one of the things that we quickly found was our initial beta testers really enjoyed the fact that they were able to take any code that they currently had in any language they currently developed things in, and they were very easily able to integrate it with Totem. Anything that speaks a basic REST communication protocol will be useful. You can immediately communicate with the service internally as well as communicate with external services. We've seen some room. I have a branch internal to the office that allows us to get a little bit of extra speed, but ultimately transference speed between local nodes is not necessarily a problem. So a couple of the things that I thought were important about Totem that we should probably drill down on. The Totem system as a whole is message-centric. There is no shared state between workers. So while you have a distributed worker swarm, none of the workers know about any other worker in the group. And this makes things a lot simpler for implementers, both myself as well as anyone who would be implementing this inside of their own local environment. You don't have to worry about maintaining any kind of concurrent state. You don't have to worry about having any kind of consensus. You don't have to worry about where anything is if a worker dies. This allows us to keep our workers as very expendable nodes. And because of the fact that our jobs are individual messages, each one comprised of a single element of analytical work, we're able to just serialize a single message. We don't have to ship individual binaries across the wire. We don't have to ship anything in any particular weird way. You're only sending a handful of bytes at any given time, and all of that's textual. And that really speeds up the ability to load new samples and perform analysis at scale. We've seen a couple of other systems that are in the streaming space that do things using either ZeroMQ or a handful of other systems that do directed transference of malware samples themselves across the distributed cloud. And that's a useful way of handling things if you're guaranteed to be inside a local network at all times, but we don't have that guarantee. One of the things that we're doing is we have a hybrid system for processing this malware. 99% of all the samples that we have, we're perfectly comfortable with processing them inside of AWS or another cloud provider. We only get a handful of samples at any given time, which absolutely have to be maintained within the control of our local environments. One of the nicer things about Totem is it allows us to scale material across a hybrid environment. Samples that need to stay local, samples that need to be run, say, a dynamic analysis system, can stay and are automatically routed to local nodes, whereas other nodes sitting out in the cloud or sitting in any kind of distributed environment will automatically consume messages that are more appropriate for them. So long as a totem worker is capable of communicating with a RabbitMQ node in this case, or any kind of distributed file system, we have a HTTP load balancer that sits in front of a distributed React CS cluster. You're able to begin processing. At the end of the day, deployment for any individual node takes on the order of maybe 5-10 seconds all told. We're overall very resilient to failures, as you have to be in any kind of distributed environment. We take best effort guarantees to be able to transfer your message, not lose work, and generally function normally. Right now, we're a at least once processing system, which means that there are sometimes instances where if you kill a worker, a specific job might be completed twice. These are fairly rare circumstances, but we can't get the guarantee really any better than that at the moment. That's not a major concern for us. At the end of the day, most of the static analyses that we do are relatively time independent, and everything that we load into our backend DBs gets timestamped. So we know if there has been a secondary run due to some component failure. But at the end of the day, it allows us to very easily make sure that we have never lost any particular element of work. And finally, because of the fact that each individual message can be serialized as a set of individual components of analytics, if we go through 4, 5, 6 analytics and the 7th or 8th one fail for any arbitrary reason, we serialize out anything that succeeded, we retain anything that failed, and we re-queue it all over again. Obviously, as anyone who's familiar with some of the distributed systems work, anything that's backed fore and front with queues is a fairly loosely coupled architecture. We found that this is very, very helpful for us. Failures we found, even in our worst scenarios, might stop processing, but at no point is the fact that we need to run particular samples ever actually compromised. And we've never failed to deliver a message, regardless of how many workers we actually kill. This is useful for us. It allows us to run things inside of AWS on spot instances, where you don't have any real guarantees, which seriously cuts down on the amount of cost that is ultimately incurred. And it definitely allows us to add new workers in very diverse environments very easily, because we're never really concerned that something might become deadlocked or something might stop or cause some kind of cascading failure. One of the things that I got asked a lot when originally designing the system and demoing it to people was, what are we doing for our language selection? What is everyone going to have to learn to be able to work with this? Now, obviously, for the analytics, we're more or less language agnostic, but Totem itself, the planner and the monitoring layer, is implemented in a JVM language, which is Scala. We chose that for a couple of reasons. I know that there are a number of systems out there that are using Python or other systems right now, but we chose something that moves away from Python for 3 major reasons. One, I want to be able to have easy, seamless concurrency without having to fight the GIL every 10 minutes, because I get really sick of that. I wanted to be able to have type safety internally, so that way if someone who's implementing a new analytic wants to ensure that data is heavily vetted before moving on to the database system, or enforce a schema on one particular area, they'd be able to do so. And in the case for people who don't want to enforce schemas, we're capable of just serializing things blindly to JSON without any kind of major issue. And then finally, we wanted to have a system that's relatively approachable. Lots of people may not like Java. I'm not personally an enormous fan of it myself, but it's very understandable syntax. Scala syntax is not necessarily substantially different, and especially in what we've open sourced today, we've gone through some fairly substantive means to make sure that everything's very clear and very approachable. So no one who's looking at it should, if you've passed a level 1 or level 2 CS class, or even been in the industry for a year or two, you should be able to immediately understand what's going on. So as I've mentioned before, scale is something of a pain, and one of the things we've unfortunately not been able to open source yet is our dynamic scaling system. We're capable of monitoring all of Totem, figuring out what our level of load is based on analytics that need to be run, or what's stored currently in the queue, or the number of analytics that we currently have up compared to what we could be launching at any given time. And we've got a system right now that allows us to monitor that material and dynamically launch more nodes whenever we have a fairly large amount of samples that need to be racked. Obviously, this does little for us in the event that we're primarily working on samples that need to remain in-house, but that's a far edge case in our environment. As I mentioned before, and as should be fairly clear by now, totem speed really comes from the ability to join workers dynamically to an existing workload. So we've generated, early on, we generated a large number of performance metrics, and these are some of the smaller sample sets compared against CRITS. Now, comparing things against CRITS might be a little unfair, mostly because CRITS is a single node system. It's completely monolithic. This was less a comparison of raw speed and more a comparison of what happens when you begin trying to analyze things under load inside of it. CRITS, number one, is obviously slower than Totem as it stands. The issues with underlying language and concurrency model. But the bigger thing that we found is when you begin loading CRITS in any meaningful fashion, any amount of load on one section of it, and be it the ingest, or be it the database loading portions, or be it the analytics themselves, causes that load to be distributed against all other portions of the system. And what we found was, as we tried to load more and more samples and allow them to run concurrently, we found very quickly that we saw increasing numbers of error. And we highlighted that here. Towards the 50,000 sample range, which is not a large number of samples by any means, we started to see CRITS begin falling over. And those errors there are errors that caused an unrecoverable state for that particular sample, forced it to be requeued, or meant that we weren't able to load data or perform the finalized analytic. Whereas with Totem, both for 3 workers, 100 workers, while our speed stayed more or less stable, we never actually saw any individual errors. In another test, even when we would try to load the system as much as we possibly could, even the worst failure scenarios had individual analytics possibly failing, but those individual portions of a job would get requeued and reprocessed at the end. So while even if you have a misbehaving job, you have a overall system that behaves slower, the system will still continue behaving, and it will complete anything that it's capable of completing all the way to the bitter end. So this graph, which is not terribly readable at the moment, represents 2 sets of Totem deployments that are running in our production environment against 1 million malware samples apiece. To run 1 million malware samples against 100 Totem nodes sitting on AWS larges, which works out to being, I think, 400, 600 cores, I can't remember off the top of my head, works into just under 2 hours. And this was running for 3 separate analytics for every single sample. And those analytics were a call to VirusTotal to check to see if VT knew anything about it, which was an external API call that goes over HTTPS. There was the application of the Yara Exchange's full Yara rule set against each individual sample. We were generously provided the access to the Yara sets. And then finally, we did a number of various hashing techniques against each binary, MD5, SHAs, feature hashing, just as an example of what you can do. So while it's 1 million individual samples, we've got 3 million overall sets of analytics that get run. And it took us just under 2 hours, more like an hour and 45 minutes or so, to process 1 million samples with 100 spot instances on AWS. So internally, we've been able to implement a large array of analytics services. We've currently got CRITS services parity internal to Novetta. We've got clear support for third-party services such as VirusTotal or anything else you may want to do an external call to. And we support resource extraction for a number of different techniques. Right now, for the open source release, we're releasing a handful of these at the moment. We're not able to open source all of them, but now that it's an open source project, we should be able to develop these again in an external environment. Finally, we're looking into support fairly soon, going through Apache Tika to do content parsing for Office, HTML, JavaScript files, which should be a useful thing for a lot of individuals who are working with more of these textual-based documents. We've even got a handful of more experimental things that are running internally. We've managed to integrate a handful of Radar instances, Radar 2, if anyone's familiar with the open source disassembler. We've been able to do that and begin pulling down some automated disassembly. Obviously, that's not a perfect solution, but it's something that we've found to be useful and is getting to be seated in a handful of other analytics that we're developing going forward. So obviously that's the planning layer, the organization layer, and the static layer. But the last thing that we have today to talk about is the dynamic analysis layer, Drakov, which is going to be presented by Tomas.
Thanks, Zach.
So as you can see, Drugfoof sits in the investigation layer of the Scald framework, and let's look at that more in detail. So the best way to describe Drugfoof is that it's an agentless dynamic analysis system. And by that I mean that you don't have to install any special software within the sandbox, within the virtual machine that you want to run the malware in. And this is very important because one of the first things malware do when they want to thwart analysis is look at the environment they run in, and if they can find a process coexisting with the malware itself, they shut down. So if you don't have anything that's fingerprintable, you are much more likely to actually be able to analyze malware successfully. So it is open source. It has been out since last October, and it's built on the libvmi library, which is also an open source library, which is effectively a wrapper around the Xen virtual machine introspection subsystem. So while libvmi itself is hypervisor agnostic, for now Drugfoof really relies on Xen's VMI subsystem, which is very robust. The three main components that I found the most important about Drugfoof is the stealth capability that I already mentioned. Monitoring is purely performed through the hypervisor using the Intel virtualization extension, so you really don't have any special software installed within the sandbox. Furthermore, it is very scalable, so we are using both copy on write memory and copy on write disk, so we can spin up full virtual machines in second, and furthermore only allocate resources for those virtual machines that are absolutely necessary, so you can really scale up the number of sessions running on a given hardware. Furthermore, you have full access to the virtual hardware of that virtual machine, vCPU registers, the memory, or even the disk, so you really have a complete view of what's happening within that virtual machine. With that, what we have been able to do is actually monitor all system calls that happen within that virtual machine, but really we can trap whatever event we want within that system. So for example, we also trap on heap allocations within the Windows kernel, and we also trap on all the scheduling events that happen. The only problem with that is if you really don't have any agent within that virtual machine is how do you actually start the malware sample, right? With Cuckoo, it's quite straightforward. You have the Cuckoo agent sitting within the virtual machine that will start it on your behalf. Well, if we don't have an agent, we don't want to have some server running in it because then that server itself could act as a red flag for malware to look for. So instead what we developed is a way to hijack any existing process within that virtual machine to start the malware sample on our behalf. So let's look at that actually in a demo. That's probably going to be easier to follow. So here I have Xen 4.4 running a Windows 7 virtual machine. And what I'm going to show you is that how to actually hijack that process, the task manager that's running within that VM to start arbitrary execution. So again, you have full access to that virtual machine, so you can actually reconstruct what's happened inside. So I just listed all the processes that are within that machine using standard memory forensic techniques. So this is the same techniques that Volatility would use. Here we are just running it on a live virtual machine. So the way we're going to hijack that process is by trapping on the events when that process gets returned from kernel mode to user mode to actually start calculator on our behalf. So as you can see from an external perspective using the hypervisor, I was able to inject a brand new process into that virtual machine without having anything but standard processes running in that machine. So again, I don't rely on Task Manager. It could have been any other process like Internet Explorer. And with that, what we effectively have is an external shell to that virtual machine where we can actually pass arbitrary commands. It's like having a terminal to that machine. So I just pass the command to start up Internet Explorer and send it to a website. As you can see, it's quite fast, and it also tells you a lot of information about the process that actually got injected. So you get the PID, the thread ID, and all the information that will identify this new process that got injected. And you can really chain together as many commands as you want. So instead of just typing in stuff, I'm just going to copy paste it here because it's a long one. So what I'm going to do here is actually start up command.exe to download a process monitor from sysinternals, unzip it, and start it up automatically. And it will hopefully work. There we go. Command injected. Zip is downloading. Extracted, and it's running. So with that, you really have a very effective external shell to that machine. The only thing we don't inject right now is keyboard and mouse events, but that can also be done. So once you actually injected the malware sample, the other thing you want to do is actually start monitoring. So this is still Xen 4.4. And the way we actually achieve monitoring of that machine is that we are going to be injecting breakpoints into the kernel. And by breakpoint, I mean the standard breakpoints that you would use when you're debugging a software. Except we configured Zen to actually trap all those breakpoints into the hypervisor. So the Intel extensions are configured that the breakpoints will trap into the hypervisor. So we can actually monitor the full execution of the Windows kernel. So still I have standard process listings. I'm also going to show the kernel modules listed. So you really have a complete view of what's happening within the machine and what's there. So yeah, this is the Windows kernel. Those are all the kernel modules loaded. And what I'm going to do is actually I'm going to start up a screen session because the output is going to be very verbose and it's not going to be able to, you're not going to be able to actually read it. So I'm going to be grabbing through that output later. So now what you actually see here is all those breakpoints have been injected into the Windows kernel. And this is the live execution of Windows running on the right. And once I start moving the mouse around, you see things speeding up quite considerably, but I mean, it's not designed for humans to really understand what's happening in there. It's like watching the Matrix. So what we are going to do is actually grab through that output for some more meaningful things to look for. First, I'm just going to grab for the instruction pointer. These are going to be the actual functions that are getting called within the Windows kernel where our breakpoints are injected. And this is how we actually are able to monitor system calls. So we are not actually trapping on the system call instruction. We are trapping on the functions that get called when a system call is issued. So these are all the system calls that Windows is executing right now. But the other thing that I'm also trapping on is heap allocations. And heap allocations are very useful features because that really allows you to reconstruct a lot of things about what's happening within that machine. So for example, as you can see, a lot of things happening even if the machine is idle. Once I start moving the mouse around, you will see a lot of I/O allocations. Maybe you can read it, maybe you can't. But these are just the coordinate structures that hold where the mouse is moving. But some of the other things that are very useful from the kernel heap that you can look for is file objects, for example. You want to see what files are being accessed within that machine, and you can do that by watching for file object allocations. So I just right-clicked on some personalization thing on the Windows desktop, and these are all the files that are actually getting accessed by Windows. And I get this list just purely looking at the memory and the execution of the machine. So I don't have anything watching the file system access itself. This is Windows trying to allocate the structures before it actually accesses those files from the file system. There's a lot of things getting accessed just for a simple thing like this. So this is quite amazing. And as you can imagine, this is very useful when you're analyzing malware, when you want to identify what files have been touched, what is with the malware doing, because you actually see all the files that have been opened. And this is not something malware can really mess with. This is really the internal Windows kernel trying to open files. So unless the malware is implementing its own file system access mechanism and its own heap allocation mechanism, effectively loading another operating system within the operating system, you can really trust this. So I just created a text file on the desktop, and as you can see, it shows up in the log as well. So this is really, really a nice tool to have. Another really awesome thing about Druckfoof, it's really cloud ready. So everything that is required to run Druckfoof has been in Zen since Zen 4.3, which has been released about 2 years ago. For Zen 4.6, I've reworked the entire VMI subsystem of Zen. So in Zen 4.6, it has been optimized, and a bunch of really cool stuff have been merged into Zen 4.6. The first RC is going to be cut in 2 weeks, and Zen 4.6 is going to be released later this year. The only thing that's stopping us from running Druckfoof in the cloud, like on Amazon, is the fact that most of the cloud providers don't enable this thing called Zen security modules, which is really what would enable us to run this system securely on a cloud deployment where there might be other users on the system. So XSM, the Zen security modules, would enable us to segregate these systems from each other. And unfortunately, most cloud providers don't enable that, either though it has been in Zen for years now. Another really cool thing about Zen is that it's running on ARM software. On ARM chipsets, so you can actually analyze mobile malware like Android malware. So I actually implemented for Zen 4.6 a basic tracing capability for Zen using the ARM two-stage paging mechanism, so you can actually monitor memory accesses that are happening on ARM chips. So you're actually going to be able to analyze mobile malware with this system as well, but it's still a work in progress. And the current status of Drugproof is actually that it's still not complete. So it's not a drop-in replacement for Cuckoo. You can't just use this and forget about it. But we are very much hoping to get this up to that stage. So right now, this is really just an academic prototype that I created for my PhD thesis to show that this is actually possible to do. And as you can see, it's quite stable. But it definitely needs community involvement. So it is open source. So if you like it, please use it. Submit patches, submit bug reports. And there are many new things coming that will be very, very nice to have for Drugproof. So for example, Intel is releasing a new chipset that will have this thing called the Intel virtualization exceptions, which will be very useful to have for Drugproof as well. I actually had a chance to work with the Intel developers to create the first open source implementation for this for Zen, which will be available in Zen 4.6 as well. So Zen on ARM is also the one that I'm very excited about. And we also want to look at KVM. So setting up Zen is a sharp learning curve. So I'm aware that a lot of people would just want to use it on KVM and it would be a lot simpler. So we definitely want to get this or a similar subsystem to KVM as well so we could actually run Drugproof with KVM. So let's look at the big picture again. So this has been all the investigation layer and our future work is really the interrogation, what to do with the data we have. So we really generate a ton of data. So some of the output from Drugproof is hundreds of megabytes of logs. What do you do with that data? I mean, analyzing just the binary itself is not going to get you much. As George said, binaries themselves are too cheap. We should not focus on just the binaries themselves. We really want to answer the 5 Ws. And the best way to do that is to create context. So based on this data, we have very verbose data. What we are hoping to do is use big data analytics tools to mine that data to determine how malware actually relates, identify families, relationships, campaign actors, who is behind the malware, and identify the infrastructure. It's a lot more effective way to shut down malware if you shut down the infrastructure instead of trying to clean up all the binaries that are out there. And also making this data available to as many use cases as possible. So we definitely need to have a GUI for humans when they want to look at this data. Like for example, the Drugproof output is pretty much unusable as a human. It's way too verbose and you can't really get much out of it. So it has to be structured as well for humans as well as for machine learning algorithms. And this is something that we want to do as we go forward. Also retaining historical data sets. So we want to keep as much data as possible, but as we go forward, that data is going to become massive and it has to remain searchable, and that is going to be a challenge. With that, I'm very happy to announce the open source release of Totem. So this is a brand new system released by Novetta. So this is what Zach wrote, and this is what Drugproof integrates with. So the 3 components of Totem that are up on GitHub are the service analytics component, the HTTP file server, and the transfer framework for the static analysis part. And as I said, Drugproof has been open source and it will remain open source, and we are hoping to go forward and develop both of these systems. And what we're releasing today is the log parser that will integrate Drugproof into the Totem framework. We also have a booth, so me and Zach work for Novetta, so please find us. We are at booth 1064. We have a bunch of other things that we would love to talk to you about, so please come and find us. And just to recap what we have showed you here is we created a blueprint to create large-scale malware analysis frameworks, systems using the Scald framework. And we created 2 systems, the static analysis component with Totem that can analyze hundreds of thousands of samples in minutes, as well as the Drugproof system, which is a stealthy hypervisor-based dynamic analysis systems. So both of these systems are open source. The links are up there. Please go and grab them. They are actually both on GitHub. And with that, I thank you for coming, and we will take any questions you have. So there are microphones in each lane, so if you have any questions, shoot. Thank you.
Hey, Tomas. So
can you ask on the microphone, sorry?
Can you break on NTDLL or just NPS kernel?
Sorry, can you repeat that? I can barely hear you.
your breakpoints, can you put them in user space as well?
Yes,
in
yeah.
kiosk
So
kernel?
for now, Drugfoof is monitoring the kernel, but you can really inject breakpoints anywhere in physical memory, which could correspond to user space applications as well. The only thing you need for that is really breakpoints, locations for the breakpoints to be placed. So if you don't have the debug information for the process, you're not necessarily going to know where to place those breakpoints that will be meaningful. But for example, if you know that a process loads libraries that you have debug information for, you can definitely monitor those usages for the user space process as well. So for now, I'm not doing that, but it is definitely possible.
Yeah. And you use the split page technique, so the reads are different than the execution?
Yeah, so essentially the breakpoints are protected with EPT permissions. So if anyone within the virtual machine tries to read from those memory locations to determine if there are breakpoints, I actually trap those accesses to the hypervisor, and I can just remove the breakpoint and tell whatever process is running within that machine that, oh, there is nothing there. And this was one of the very first things that we had to do, because Windows actually blue screens when you just inject breakpoints into it. So, so that was one of the very first things we had to do to actually just not crash the system. So it's actually, the breakpoints are invisible. So you can scan the physical memory from within the machine, but you will not find anything.
Thanks.
Yep, no problem.
Is it on? Two questions real quick. Are you handling 64-bit malware on 64-bit OSs?
Yeah, so right now Drugfoof supports both 32-bit and 64-bit Windows. The user space component doesn't really matter because I'm really trapping the kernel itself. So, but yeah, I can do it with both 32 and 64-bit. So.
And when you do your dynamic testing, how long is your test run for?
It depends. For my test that I did, I usually ran malware for 1 minute, but it's an arbitrary number, so you really have no idea how long you have to run malware for. So I'm not doing any timing manipulation here to, like, try to skip sleeping malware or anything like that. So this is just, if you want to run it for a year, you can. I run it for 60 seconds if I see something interesting, but it's an arbitrary number. There is no solution for really determining how long you need to run malware before you actually observe anything malicious. That's an open research problem. Well, thank you again for coming.